Next, they introduce virtual memory, and they talk about the model of virtual memory. So they talk about the process of address translation that I just explained before. But they also specify that very important aspect of address translation that I have skipped earlier. And here what I want to explain it to you. And that is this translation process also combines with caching. So let me explain what I mean. Imagine you want to translate an address. Okay, so let's say you want to access a memory location, say AI. Let's say AI. And the location, this memory location has address 000. So let's say all zeros. So let's say you want to address an address that is all zeros. Okay. Let's forget about this sign extension. This is specific to 64-bit architectures. So you have an address that is all zeros, and you want to know where I can find this address, this location in the physical memory. So this address 0 is actually a virtual address, and we want to get the physical location. So you look at the root table. So this is the root table. You look at the row 0 of it given by these bits, which is going to be, say, this row. This row has a location of the next table as well as a translation of this address. So the translation we don't care about. They will substitute these bits with some other bits, but it would forward the translation process to some other table. In that table, we look up these bits. Again, it's going to be this row. And that forwards us to another table, for example, that table. So we look up this table. And again, we'll look up these bits, which are all, assuming in our example, all 0. So it's going to be the first row of this. That takes us to another table. And finally, we're done with the translation. Okay. So the one memory lookup of address all 0 has been turned into 1, 2, 3, 4 memory lookups. But as I explained, as I mentioned earlier, these are cached. Let's see what this means. Imagine you want to translate another memory location, which is this is all 0, this is all 0, this is all 0, and this is say all 1s. Okay. What this means that in terms of virtual address, these two addresses are very similar. In other words, these only the lower whatever 16 bits of this memory locations are different. Like they could be within 16 kilobytes of each other. So they're relatively close in the virtual address. How does the translation process for the second address go through? So how does the translation for the second memory location go through? So I'm going to do this with blue. So we look up, okay, so this is the second address. So we look up these bits. These are the same bits as before. So we're looking at the first row number 0 of the root table. That takes us to the same table. And remember, this is cached now. I mean, the root is always cached. But this table is also cached. We just looked it up for the green address. Again, we're going to look up this entry. Again, this entry is also cached, which takes us to the same table here, which is also cached. So these are all exist in our CPU cache. Again, this location is also cached. This is also cached, and then we look at this, and this is also cached. Okay, which means that if the translation of the second address, all of them are fast translation. Okay, fast, all the way fast. So these address translation is going to be fast. So now let's look at another address. So let's say, just give an example, we have an address that is 0, 0, 0, and now these guys 0, 0, 0, these ones are 1, 1, 1, 1, 1. Okay, so let's look at the translation of this yellow address. Whoops, I moved my screen. Okay. This red address, sorry. Again, the first bits are 0, so again we're looking at the first row. So this is cached. That takes us to second thing. This is also cached. We're looking at these bits. That takes us to this table. In this table, we're not looking at the first row. We're looking at the last row, right? Because the address is all 1s. So we're looking at this row. That might take us to a completely different table that is not cached. So this lookup will be fast, but this lookup will be slow because this needs to go to the main memory and it needs to be fetched from the main memory. In other words, how fast a translation is depends on how far away the address is from the address that we have accessed before in the past. So in the past we have accessed these green addresses, but this red address is too far away because these bits are different between the green address and the red address. So the red address becomes a little bit slower. The extreme case is that I access a memory location that is different. These top bits are different from this. When that happens, I will be looking at a completely different row of the root table. That might take me to a completely different table, and these entries are not cached. So this is already gonna be slow. So, and then that takes me here. That also could be slow, etc. So compared with having, let's say, 4 fast memory lookups, I could have 1 fast memory lookup followed by 3 slow memory lookups. So that's the difference between the translation of different addresses. And what do I expect this to have? What do I expect its impact to be in practice? The impact would be if I'm accessing memory locations that are close to each other, if the access will be fast. But the further away I access in the memory, the slower it gets. And it has nothing to do with cache or the usual cache as we think about them. This is due to the table lookup cache. Okay, so that's what the theory will predict. But let's see how they capture it in terms of the actual theory. So what they do for the model is that they introduce these extra parameters. Okay, so they have a page size for how big the tables are, how many bits of translation we do at a time, how deep we go into translation, how big is the cache, and what is the cost of a cache fault. So this is a relatively complicated model, I would say, because it includes all these extra parameters that are, so we have like 5 extra parameters. But on the positive side, on the plus side, the algorithm we're trying to analyze could be very simple. I'm going to skip to the analysis because it takes quite a bit of time for them to get started. Yeah, I'm going to skip a whole bunch of analysis here. Let me just get to the actual result if I can find it. Okay, analysis of the algorithms, sequential access. So sequential access is very simple, but I'm going to skip this. I'm going to go to random access. Okay. This random access cost is quite interesting. The cost of a random access is going to be quite high. So you have essentially a log factor here. And this is important because random access in theory should be linear time, right? Because we're just accessing every element of an array exactly once. So we have, we have this linear term. We have n, but it has 2 extra factors. So this is constant. So this doesn't change too much. But this part is interesting. So it's this part that we want to pay attention to. What is this? So this is a log base k. Again, k is a constant or is a fixed parameter in the architecture. Doesn't depend on the input. It's the how many steps, how many bits we translate one at a time. And again, these things are fixed by the architecture, but this part is variable. What this tells you is that if you take the running time of random access, so this is the time of the random access, and this is n. If we divide it by n, what this analysis shows you is that you're supposed to get this factor, right? You're supposed to get tau log base k of n divided by pw. Okay. If there was no factor n here, this running time would have been a constant. Oops, what about that? Exactly. Okay. If there was no n here, this running time would have been constant, then I would have seen like my theory would have predicted like something like this. But there is an n there, which means that this is going to be a slowly growing function. So it's going to be like a log function, but it's going to have a slow slope. And this is going to increase as I increase n. So now the question is, do I see this if I go back to the experiments? So let's go back to these experiments and we'll see if this is visible in the picture. Okay. So random access. So this is random access, it's this guy. So we'll see that random access essentially has this stepwise behavior. And if you remember, the cost was like it was tau times log base k of n divided by pw. And this also shows why we see this jagged behavior, because this log is actually an integer. This log factor depends on how deep we go in the translation step. This log factor needs to jump with how n is. So ideally, I would like them to have followed up to see that these jumps that we see in the experiment. So we have a jump at this point, maybe we have a jump at this point or at this point. What I want to know is that whether these input sizes correspond to the value predicted by the theory. I don't think they do this in the paper, but for this theoretical analysis to be 100% convincing, they need to show that this behavior is 100% consistent with what they claim. But at least it's interesting that the model predicts that the running time will get slower the larger n is, which is what we observe here. And at this point, at this part of the picture, there are no cache effects because these inputs are very, very big. It's like 2 to the 27. That's a very big input size. And if it's only cache effects that exist here, we should see nothing here. We should see nothing interesting here. But it's interesting that's what they predict. And similarly for all the other algorithms, they do similar analysis. Again, we don't want to delve too deep in this because this is just an example, right? So they do analysis also for the binary search. They obtain similar formulas. It's a little bit harder to understand. The interesting about binary search is that binary search becomes a log squared algorithm because there is this log factor from the binary search, and there is also this log factor from the same term that we observed. And etc. Like all these algorithms essentially gain an extra log factor except for sequential search. So if I go back to the sequential algorithm, the sequential algorithm has no extra factors, right? So essentially it has only a factor n, there are no extra factors. So this model predicts that if you divide the running time of sequential search by n, you should see a straight line. And that's, if you remember the experiment, that's exactly what we see. So all in all, the results of the experiments with the theory is consistent, but it would have been nicer if they could go a little bit deeper and if we could follow up more experiments in the paper. But I guess not everything can be perfect. So that's one example of how algorithm engineering can be used to bridge the gap between theory and practice.